Hi, class. Today I wanted to talk about the chain rule with you. Sorry I had to record this. I have an ortho appointment that I have to get to, and I didn't want to cancel class because this is a pretty important topic, and I wanted to give you some time to work on it between now and Thursday. I didn't want to wait till Thursday. So let's see. I am sharing. I am recording. Excellent. So far we've talked about finding simple derivatives. Today we're going to focus on finding the derivatives for composite functions, which requires the chain rule. You're going to be using this a ton to find your derivatives. My setup is a little different down here. I usually am upstairs, but because everyone's sleeping, I'm in my kitchen. So I'm also on my laptop. So apparently the new software is different. So hopefully everyone can see this just fine. In order to talk about taking derivatives for composite functions or using the chain rule, it's really important that we understand when we need to use it. So first of all, I'm going to say that the chain rule is used to differentiate composite functions. Now, you guys learned about composite functions in college algebra or algebra 2, whichever you had. If you don't remember what a composite function is, I'm going to remind you right now. So let's come up with a list of functions that are not composite. And then we'll look at their counterparts that are composite. Okay. So an example of a function that's not composite would be something like f of x equals 2x plus 1. This is the kind of function that we would have differentiated in the last chapter. We would have just taken the derivative using the simple power rule, or technically just the constant multiple rule and the constant rule. A composite variation on this would be where we would have an inside function and an outside function. So maybe this function would be inside. So something like 2x plus 1 to the 5th power. So this is a composite function. For this function, it's like you're taking f of g of x, where f of x is x to the 5th, and g of x is 2x plus 1. So remember back when you were in college algebra, you learned how to take composites of functions. So you were given, for instance, f and g, and you were asked to find f of g of x, and you also saw it as f of g. It looked like fog. But when you did that, you took your outside function f and your inside function as g of x. So your f function, your outside function, was taking the inside function to the 5th power. So you took your outside function, and everywhere you saw x, you swapped it out with g of x. So instead of having x to the 5th, you had 2x plus 1 to the 5th. So that's where you originally saw these composite functions. But notice that you can't really do that in this case. You wouldn't really have necessarily an inside and an outside function as clearly as you would over here. So that would be an example of a composite function. Another function that would be not composite that you would have seen in the last chapter would be something like f of x equals the cosine of x. So if f of x is equal to the cosine of x, you don't have an outside and an inside function. The difference for this section and using the chain rule is you're going to be looking at functions that are, instead of cosine x, it'll be something like the cosine of 2x. So in this case, your inside function would be 2x, and the outside function would be cosine x, if you were to compose two functions together to create that. So not a composite function. This one's composite. This one would require the chain rule. Let's see. Another function that you would have seen previously would be something like f of x equals e to the x. And in this section, when we see an exponential function, it might be something like e to the x plus 1. So that would be an example of a composite function where the g of x is in the exponent. Another one that you would have seen for trig, not composite, would be sine x. And a composite variation on this would be sine squared x. Because remember, when you're writing sine squared x, it's really the sine of x squared. So now you can clearly see this inside function as being sine x. So usually I recommend that if you have these trig functions where your exponent is written in between the function and the variable, that you rewrite it so that you can clearly see that you have that whole function being taken to a power. So this is not the same, of course, as the sine of x squared. Not the same. Oh, sorry. Not the same as the sine of x squared. I oriented my camera differently here because I was so afraid I was going to knock it off the island and never see it again because it would break. I would see it, but I would see it in like broken pieces. So I put it up here, but now it's at the top. So I'm going to have to kind of see how that works for me if I have enough room to kind of scoot this over. The zoom was also different up here. So let's see, maybe if I do this and kind of work my way up. Okay, we'll try. I mean, it's a work in progress. Okay, so we're going to talk about the chain rule, what it is, and how we're going to use it to take the derivatives of composite functions. So first, I'll give you the definition of the chain rule. We're going to be using this throughout 3.1. And this also, by the way, is in your book on page 208, in case you're looking. But this is a theorem, the chain rule. If f and g are differentiable, then the composite function f of g of x is differentiable and f of g prime, or I should say f of x, f of g of x quantity prime is equal to f prime of g of x times g prime of x. Now, when we actually are applying this to actual derivatives, I don't necessarily, I mean, yes, this is essentially what you're going to be doing, but each type of function is going to look a little bit different. So basically what you're going to do is you're going to take the derivative as though it was not a composite function. So ignore the inside function while you take the derivative. Just take the derivative normally, and then you're going to have to chain on the derivative of the inside function when you're done. So chain it on just means multiply it by the derivative of f of g. So most of these aren't too crazy. The big thing about the chain rule is just knowing when it's necessary. I think that's a lot of the problem that people have here, is just recognizing when you have a composite function and when you need to chain on the derivative of the inside function. It seems like so many people need to use the chain rule and they just kind of gloss over it and take the derivative normally as though they don't need to even use it. So that's the biggest problem I see with the chain rule. Not that people can't use it, it's just that they don't know when it's time. It's really important to know when it's time to use the chain rule. Okay. So let's, oh, one more thing I wanted to go over real quick was this, it's this power rule that your book loves to split up so many ways, but we're going to use it real quick. So I just want to bring it to your attention. It's a theorem, power rule for functions. And Aiden is probably wondering, like, ooh, is this when we're going to talk about taking a function to a rational power? No, you're still not talking about it yet, so stay tuned. Right now, we're still talking about integer powers. All right, so here's your theorem. If g is a differentiable function, and n is an integer, then the derivative with respect to x of g of x to the nth power. Okay, so the difference here between this power rule and the one you saw before is this time we're not just taking x to the nth power, we're taking some function g of x to the nth power. Okay, you're going to bring the exponent down, multiply it by the inside function g of x, decrease 1 from the exponent, and then chain on the derivative of the inside function. So if you're wondering, like, wait a second, how is this different than that? Well, the chain rule is general, and it's going to apply to a lot of different families of functions. We're going to talk about several different types today. And this power rule is really just applying to power functions. So when you have an integer power. And we'll get to those rational powers eventually, I promise. They can't avoid it forever. So let's talk about some examples where we would apply this. Okay, can I do this? Maybe. We get a weird angle. Whoa! You guys, I'm working on it in here. I would love to do more like math lessons from the kitchen. Okay. I think I just twisted this funny. All right, we'll try that. See how that goes. Okay, example 1, differentiate. A. So the first function we'll look at is 1 over 2x plus 1. Now, some of you are looking at this and wondering, like, why is she talking about this function with the chain rule? This doesn't make sense. Didn't we already do this when we talked about the quotient rule? We did. But you know what I really like? I really like to use the chain rule when the numerator of my rational expression is an integer. So if I don't have a variable in the numerator, personally, I find it easier to just use the chain rule with this function versus using the quotient rule. Now you could use the quotient rule, you would do f prime g and f prime would be 0. So f prime g would be 0 and then minus f g prime. No big deal. And then you'd be able to cancel something out when you were done. But if I were you, if the numerator is an integer, non-variable, I would rewrite this function as 2x plus 1 to the negative first power. So it's like this whole entire quantity in the denominator comes up. And right now you can think about it as being to the first power. Well, when you bring it up, remember you switch the exponent to become negative. Now, you can always do this with the quotient rule. You're not forced to do this way. I just think it's easier. Now you can clearly see that you have an inside function here. So what you're going to do to use the chain rule is we're actually technically using this little subset of the chain rule, which is the power rule for functions, because right now we have g of x to the n. N is an integer. So n is -1 in this case, and then our function g is just this polynomial g of x. So let's go ahead and bring our exponent out front. So we're bringing the exponent down, and then we're rewriting the inside function. So don't mess with the inside function yet. Remember what I said, take the derivative normally until you get to the end. So just ignore it for a minute, just write it down, but act like nothing is weird. Nothing is happening here. And then decrease the power by 1. So -1 minus 1 is -2. Now, this is the way you would normally take a derivative if you just had x to the negative first. But you don't just have x to the negative first. You have 2x plus 1 to the negative first. So what you need to do then is chain on the derivative of the inside function. The derivative of the inside function, 2x plus 1, is 2. Now, when you rewrite this, because you can't leave it like this, you can multiply the -1 and the 2 to get -2. And then in the denominator, you can make that exponent positive. And of course, you could go back and check this and verify that that's exactly what you would have gotten if you would have used the quotient rule. But you can kind of see that by looking at it. Had you used the quotient rule here, we already said that f prime g would be 0, and then you'd have minus f, which is 1, and then g prime, which is 2. So that's where that -2 would come from. So feel free to verify that as an exercise on your own. Certainly not something that I will require you to do, but that's how we use the chain rule. So we're going to use it a lot today. And you're going to get really good at it because you're going to need it in most of your derivatives here on out. Sorry. So let's do another example. Let's do example B. Oh, by the way, I'm writing on notebook paper today because we ran out of plain white paper. So hopefully the lines aren't driving you crazy. Maybe it's better to have lines. We'll see. Okay. Get my focus going on here. Focus. Okay. We'll just write and then fix it. It might fix itself. It does that sometimes too. All right. Our next function will be f of x equals e to the x minus x cubed to the 6th power. Oh no, that's terrible. There we go. Okay, f of x equals e to the x minus x cubed to the 6th power. So we're going to use the chain rule here. Clearly, I hope we can see that we have an inside function and an outside function. Our outside, if you were thinking about it, would be like x to the 6th power. But what we're going to do is we're going to take the derivative the way we normally would, and then we're going to chain on the derivative of the inside function. So the way we would normally take a derivative here is we would take our exponent, put it out front, rewrite the inside function, decrease the power by 1. And the difference here is we don't just have x to the 6th, we have some function of x to the 6th. So it's not just 6x to the 5th now. We need to go ahead and chain on the derivative of the inside function. So the derivative of the inside function is going to be e to the x minus 3x squared. Okay, so this was your inside function. And then this was the derivative of the inside function. And honestly, there's not a whole lot you can do to this one. If I were you, I'd probably try to simplify it a little bit just by multiplying the 6 into this derivative. So I'd maybe say, okay, we have 6 e to the x minus 18x squared, and then e to the x minus x cubed to the 5th. What I don't want you to feel like you have to do is take e to the x minus x cubed to the 5th power. I don't want you spending all day long on crazy algebra. This is fine. Leave it. Just simplify as much as you can and then be done. I think it's actually the lighting in my kitchen that's causing a problem. When I scan stuff in here, I have this problem too. Okay, do the best we can. All right, so that's example B. So nothing here inside was a new derivative. We'd already knew derivatives for e to the x and x cubed. So The only new thing here was that chain rule. C, do one more of these. F of x equals negative 5x divided by, in parentheses, 4x minus 1. And then that quantity will be cubed. Okay. Now, you have an inside function in your denominator. There's a composite function going on here. It's not just x cubed, it's a function of x that's being cubed, 4x minus 1 cubed. But you also have in the numerator some function of x. You don't just have a constant like we did in example A. If we did, we could just rewrite this as a product and do a constant multiple. But we don't have that. So we're going to have to use the quotient rule here. But we're going to have to combine the quotient rule and the chain rule because the derivative of the denominator is going to require the chain rule. So here we go again. If you want to call it h, then we can consider f of x to be our numerator, and g of x will be the denominator. Let's do it that way. Then we'll say that f prime, since we're going to need all these parts here to use the quotient rule, is negative 5. And g prime is where we're going to use the chain rule. So if our denominator is g and we're trying to find the derivative, well, this looks very much like what we did in the last two examples. We're going to bring the exponent out front. We're going to rewrite the inside function, take it to the n minus 1th power. So 3 minus 1 gives us 2. And then we have to chain on the derivative of the inside function. So the derivative of the inside function, 4x minus 1, is 4. Now, since we're going to have to put all this together when we use our quotient rule, let's just go ahead and simplify as much as we can. Don't bother expanding out the 4x minus 1 quantity squared. You might get lucky and end up getting something that'll cancel. That usually happens. So this will be 12 times 4x minus 1 quantity squared. Whoops. There you go. Okay, so now that we have f, f prime, g, and g prime, let's go ahead and put all of that together using the quotient rule to find the derivative of h. Okay, so we're using the quotient rule here. So we're doing f prime g minus fg prime divided by g squared. So f prime is negative 5. F prime g. G is 4x minus 1 quantity cubed minus, oh, and if you're keeping track, here's f prime g minus f. Well, f is negative 5x. And then g prime. So g prime is this guy. Whether you want to do 2 sets of parentheses or 1, that's up to you. I'm just going to take each one of these factors and put them in parentheses. So we'll have minus f prime g minus f. There it is. And then g prime was 12 times 4x minus 1 quantity squared. And don't forget, you must divide then by g squared. We get so carried away with doing our quotient rule in the numerator with the chain rule that we don't want to forget about the denominator. So g squared, well, 12 squared is 144. And then 4x minus 1 squared is going to be 4x minus 1 to the 4th power. Oh, you know what I did in the denominator? I thought that looked funny. I put g prime squared in the denominator. You guys, I mean, it is like midnight and I'm very tired. Walking around on a broken foot is very exhausting. And it's if I have to go upstairs to get one thing, I come back down and I'm like sweating. I mean, it's awful. And I'm in shape too. It's a lot of work. All right, g squared is 4x minus 1 cubed, and then we'll square it. Okay, so there's your g squared. Now we have to simplify. But remember that I said you would probably get something to cancel? Well, that happens when you have the quotient rule and you use the chain rule. So we'll simplify this down a little bit and then we'll cancel, because you can see that in each one of these terms, you have a common factor of 4x minus 1. Okay. This one I'm going to leave here for right now because I'm certainly not going to cube 4x minus 1. I wouldn't even want to at this point. I have a minus a negative, which is a plus. 5 times 12 is 60. Then I have this factor of x, 4x minus 1 quantity squared, divided by, and remember in the denominator, when you take a power to a power, you multiply the powers. So 3 times 2 gives you 6. Now you have to simplify this, but of course, if you were doing something like this on a test and you had all of this filled out, that's most of the work right there. The simplifying is algebra. It's important, but that's not where the bulk of your points are going to come from. Okay, now I have 3 terms. 1, 2, 3. Sorry, that circle should have included that cube. Look at each one, see what's in common. If you want to factor it out, that's fine. You don't have to, though. Notice that you have 4x minus 1 to the 2nd power here, to the 3rd power there, and to the 6th power here. So what you can do is you can take out 2 powers of 4x minus 1 in each term. So if I take out 2 powers here, both of these are going to go. And if I take out 2 powers here, well, 3 take away 2 leaves me with 1 power of 4x minus 1. And in the denominator, if I take away 2 powers, I had 6. Well, now I have 4. So let's rewrite what we have. Now that I only have 4x minus 1 to the 1st, I'm going to go ahead and multiply this in. So I have negative 20x plus 5 plus 60x. And remember that I canceled out both of these factors of 4x minus 1. So I don't need to worry about that anymore. Divided by 4x minus 1 to the 4th. And then we're almost done. We just need to simplify this addition by combining like terms. You'll have 40x plus 5 divided by 4x minus 1 to the 4th. And if you're wondering, like, do I need to do anything else here for this one? No, because, I mean, I certainly don't want you to take 4x minus 1 to the 4th power. And other than that, I mean, you could technically factor, but there'd be nothing to cancel it with, so I probably wouldn't waste my time on it. But that's just me. But yeah. All right. Something weird in my notes that I'm going to get rid of. 2, 2. Okay. Just don't want to look at that again. Excellent. Okay, so that was an example of the quotient rule and the chain rule together. You're not going to see a ton of that in this section, but you'll see it a little bit more when we work on curve sketching, and you'll see it again in Calc 3 even. I remember one summer when I taught Calc 3, I had all these students from U of I in for the summer, and they could not take these derivatives and second derivatives. They were just like, what's happening? Why can't we do this? And I was like, yeah, why can't you? You guys are all engineering majors at U of I. Like, what happened? Did you forget how to do this? Oh, never did figure out what the problem was there. All right. Anyway, they were such nice kids, though. Let's talk about trig functions, which I know you guys are really excited about, as am I. Trig functions. And, you know, these are not going to work so much differently than they did before. It's just that now we're going to be applying the chain rule to them, but sometimes students have a harder time seeing a composite function with a trig function. So I'm just going to give you these rules. I mean, they're really pretty self-explanatory, but I'm going to give them to you anyway. So the derivative of the sine of u of x. So instead of just saying sine of x, we're talking about the sine of u of x, meaning some function of x, like, you know, sine 2x, sine 3x squared, something like that. Is the cosine of u of x times the derivative of u with respect to x. Now, you're going to see that all of these are going to work the same way. So for cosine, if I'm taking the derivative of the cosine of some function of x, well, that's just going to be negative sine of some function of x times the derivative of u with respect to x. So remember, if it's a c function, its derivative is negative. So we have that. We also have a rule for tangent of some function of x. Our derivative would be secant squared u of x times the derivative of u with respect to x. So nothing super groundbreaking here. Cotangent, it's a c function. We'll have negative cosecant squared u of x du dx. And then the last two will be for the secant of some function u of x. The derivative of the secant of u of x will end up being the secant tangent. So the secant of u of x times the tangent of u of x, and then times the derivative of u with respect to x. Sometimes that one throws people just because they don't realize that you're going to apply the function twice. But that's the case. And then for the cosecant of u of x, it's a cofunction. Its derivative is negative. So you have the negative cosecant u of x cotangent u of x du dx. Okay. So I'm going to give you a couple of examples for these trig functions. Nothing too crazy. This will be example 2, differentiate. Okay. Example 2, differentiate. The first one will be f of x equals the cosine of 4x. Yeah, it's just the light. If I'm taking the derivative of this function, it's very important that I note that I have an inside function here of 4x. So when I take the derivative, I'm going to take the derivative normally to start out. The derivative of the cosine is the negative sine. I'm going to keep my inside function just the way it is. And then I'm going to chain on the derivative of the inside function. And what that's going to look like is really this. That means that this 4 is going to get multiplied by the sine function, not by the angle. So it looks like this, negative 4 sine of 4x. Let me tell you what it does not equal. Negative sine 16x. Don't do that. Not the same thing. you're not multiplying the derivative by the angle, you're multiplying it by the trig function itself. So don't multiply here. I see students do that all the time. They just take the derivative. I mean, I'm glad they're using the chain rule, but then they simplify it wrong. So the 4 gets multiplied in front, not into the angle. So there's that. I was going to do a tangent. I guess we could, but let's do a secant, because I was just saying that students seem to have a harder time with the secant just because, I don't know, it looks weird to them. So let's do the secant of 3x minus 2. Okay, so start out taking the derivative normally. So normally if you're taking the derivative of secant x, you would be doing secant x times tangent x. Do the same thing here. Secant 3x minus 2 times the tangent of 3x minus 2. And if you want to use brackets, you'll probably be more successful because it will help you to see where that constant multiple is getting applied. But remember to chain on the derivative of the inside function. Now, the reason I think people have a hard time with this is because they see the inside function twice. Don't worry about it where you see it twice. Just focus on what the inside function is. The inside function is 3x minus 2. Its derivative is 3. When you chain that on, all that 3 is doing is it's getting multiplied by the function one time, not 2 times, just once. So this derivative actually looks like 3 times the secant of 3x minus 2 tangent 3x minus 2. And it can just sit there. These are all just factors, not a big deal. Whatever you do, don't multiply it into the 3x minus 2. That's not where it goes. Okay. There's that. And then let's do one where you're taking a trig function to a power. Seems like it focuses better if I, no, I don't know. I mean, it gets there eventually. Okay. So this one will be the cosine to the 4th power of 5x. Now, I always recommend that you rewrite these functions where you have a trig function to a power. What this really is the cosine of 5x quantity to the 4th power. If you don't rewrite it, it's going to be hard to see your inside function. Rewrite it. And I know you're probably wondering, like, well, if it looks better this way, why do they give it to us like this in the first place? I don't know. For simplicity, I guess, is the way they just write it, like shorthand. I don't make the rules. I'm just trying to explain them to you. All right, so we're going to take the derivative the way we normally would using this power rule. We're going to take the 4 out front. We're going to keep the inside function the same and decrease the power by 1. The difference here is that we need to multiply by the derivative of the inside function. That's where your trig derivatives come in. And this also requires the chain rule. So if you want to call it g of x, if you want to look at it separately, that's fine. You're going to get a lot of practice doing this, and you're going to get pretty good at taking the derivative of cosine 5x, I hope. That's the goal. But for right now, if your inside function is cosine 5x and you're trying to find its derivative, well, I mean, look at what we just found. Cosine 4x is derivative up there. So very similar. G prime is going to be negative sine 5x times 5. So that gets multiplied or chained on at the end here. So negative 5 sine 5x, these parentheses, I guess, double parentheses. And then you're going to simplify. And this will just simplify by multiplying these constant multiples together. So this will be negative 20. I'll keep with my bracket notation, I guess. Cosine 5x cubed times, and you don't have to write the multiplication sign, that's totally up to you, the sine of 5x. There's your answer. So a little bit more going on with that one because it required 2 uses of the chain rule here instead of just 1. So we use the chain rule here to take the derivative of the inside function, but the derivative of the inside function also required the chain rule. So we brought the power out front, kept the inside function as is, decreased the power by 1, and then we multiplied by the derivative of cosine 5x to get us here. So that's what you're going to see for the trig functions. You're not going to see too many crazy things in this section. I kind of looked through to see if there was a bunch of chain rule inside chain rule, and there wasn't a whole lot of that going on. So, so that's good. Exponential functions. The derivative with respect to x of e to some function u of x is equal to e to the u of x times du dx. The du dx is not in the exponent, so you're taking e to the u of x and then multiplying that expression by du dx. And I'll show you some examples of that. And you know, these exponential functions aren't too crazy. They're not too crazy here either. Example 3, differentiate. So first we'll look at f of x equals e to the 3x squared minus 5x plus 6. All right, so we have e to some function u of x. Let's go ahead and take the derivative, f prime. I'm going to take the derivative the way I normally would. The derivative of e to the x is e to the x. I'm just going to hang on to this function for a minute. And then I'm going to multiply this whole expression by the derivative of the inside function. The inside function in this case is the one that's in the exponent. So the derivative of 3x squared minus 5x plus 6 is 6x minus 5. Now, technically, your answer is fine just like this. You don't have to rewrite it. I certainly wouldn't want you to distribute. Whether or not this factors in front or behind, it's fine. There aren't a whole lot of ways to write this that are so much better than any other way. So this is fine. Let it be. It's done. I know it seems like you didn't do much there, but that's good, right? These exponential functions aren't too crazy. Next, we'll do e to the 1 over x cubed. So it's 1 over, and then x cubed is in the denominator. I try not to write slash notation, but writing by hand, it's, I think, easier to see it that way. Okay, I would rewrite your original function to have a negative exponent, because otherwise you are going to end up using the quotient rule, and nobody wants to do that. So rewrite this as e to the x to the negative 3rd power, because we know that 1 over x cubed is just x to the negative 3rd power. Okay. Okay, and then once you rewrite that, this will become a much easier problem. I think looking at this, it's kind of intimidating, but just rewriting it, just taking that small step really makes it look a little bit clearer. Okay, so when you're taking your derivative, f prime of x, take the derivative the way you normally would. The derivative of e to the x is e to the x. So we're just going to keep this as e to the x to the negative third power. And then we're going to multiply this by the derivative of the inside function. The inside function is x to the negative third power. Its derivative is, bring the power down, negative 3 x to the negative fourth. Remember, your inside function with your exponential is always what's in your exponent. Oh my gosh, my leg's falling asleep. Oh, I think, I don't know, there's like no feeling in it. Okay. This is bad. I don't know. Okay. All right. So do you need to rewrite this? Not great. I mean, I would, but I don't think I'd take off points for something like this. But personally, I think it might look a little bit better if you just kept it in its original form where it had positive exponents. But I don't know. Maybe you don't think that looks much better. Everyone's got a different opinion on that. But I would say this is okay. Probably move the negative 3 out front or something. I don't know. There's not a whole lot you're going to do that's going to make this look awesome. Something like that. Okay. Do I have another exponential? Oh, I do. I do. Okay, so next we'll do C. C is f of x equals 3 e to the 2x plus 4 e to the negative 3x to the third power. All right, I'm going to have to stand. That's okay. Nobody cares. I mean, I'm on one leg, so I don't know how long I'm going to last. All right. Okay, clearly I think we can see an inside function and an outside function is just some value that's being cubed. So use your general power rule here. Bring that 3 out front, rewrite your entire inside function, decrease the power by 1, and then take the derivative of the inside function. If you want to call that g of x, fine. That means that g prime of x is going to be the derivative of this whole thing, the inside of your parentheses. We just did a bunch of derivatives of e to the, I don't know, ux. Did we do like an e to the constant? Well, we had an example 3a down here, e to the 3x squared minus 5x plus 6. And when we took its derivative, we just took our function e to that power and we multiplied it by the derivative of the inside function. That's what we're going to do here. So our derivative will be 3 times, and the derivative of u of x is 2, and then e to the 2x plus 4 times, and the derivative of u of x is negative 3, and then e to the negative 3x. Now that's the derivative of the inside function that we're going to chain on over here. It's not going to look beautiful, but do the best we can. So 3 times 2 gives us 6, and then we have 6e to the 2x minus 12e to the negative 3x. And if you're thinking, like, how can I possibly leave this like this? Shouldn't there be more that I can do here? I mean, yeah, but how much effort do you want to put into simplifying this? And personally, as your calculus teacher, I don't want you sitting there doing a bunch of algebra work that you don't need to be doing. Yeah, we all could use some more algebra work in our lives, but at some point we gotta let it be. I'm testing you on your ability to find a derivative here, not to sit here and square this quantity, FOIL it out, multiply it into this binomial, multiply everything by 3. I mean, that's crazy. This is okay. Yeah, I get it. It doesn't look that simplified. It's fine. Stick a fork in it. It's done. All right. Let us see. All right, so those were derivatives for, oh, wait, oh, I have one more. Oh my gosh, I almost forgot. Another exponential function. Oh my gosh, I'm so uncomfortable right now. Okay. All right. Try to get through it. F of x equals the cosine of x e to the negative 3x. Ooh, do you know why I'm excited about this? Clearly, it involves the chain rule and the product rule, because when I take the derivative of the inside function here, I'm going to have the product of 2 functions of x. But I'm going to ignore it for a minute while I take the chain rule, and then I'm going to worry about it when I have to chain it on. Okay, but clearly I hope we can see that we have a main trig function and then we have an inside function. So when we take the derivative of the cosine of x, we get negative sine x. We're going to start out the same way. The derivative of cosine x e to the negative 3x is going to start out negative sine x e to the negative 3x. But you must chain on the derivative of the inside function. Now, the inside function is this one. That will be your g of x, if you want to think about it that way. And then this requires the product rule. Because you are multiplying together 2 functions of x. All right, so to get g prime, oh, it's also going to require the chain rule too. I didn't even think about that, because this guy is going to involve a chain rule usage. All right, g prime of x is going to be, oh gosh, f prime g plus f g prime. And I'm reusing my variables again, but I'm not going to label them. You guys should have a pretty good handle on the product rule by now. F prime, the derivative of x is 1, g e to the negative 3x plus f, which is x, and then g prime is going to be, and we did this a couple times up here already, e to the negative 3x. We even did it up in this one, negative 3 e to the negative 3x. That's what's getting chained on here. So this is a place where you might need to pause your video and sit here and look at this for a minute and make sure that it makes sense to you. But if this is your inside function g, this is its derivative g prime. So we took the derivative the way we normally would. The derivative of the cosine of x is the negative sine of x, but we didn't just have x, we had u of x, some function of x, f of g. So we multiplied it by the derivative of x e to the negative 3x. Holy cow. You guys, I'm not managing this well. I'm terribly uncomfortable, and I can't stand. And then we multiplied it by the inside function's derivative. Okay. Do you need to simplify this more? I mean, I don't know. What else? I mean, what else are you going to do to it? Not much. What did I do to it here? Oh, I took out like an e to the negative 3x. Okay, I'll show you that just because in case you see the answer written like that in the back of the book or something and you're like, how did they get that? Let's say you left this part right now by it alone. It's e to the negative 3x. And then you factor it out over here, e to the negative 3x. Well, that would leave you with 1 minus 3x. You could do that. There are a lot of different ways you could write this. Then you could multiply over here by any number of things, but I guess just to keep it simple, you could do something like this. I mean, there are a lot of ways to rewrite this. I'm not super worried about that. I just want to make sure you can take the derivative using the chain rule and get it. And anything obviously that needs to be anything obvious that should be simplified, do it. But nothing here is like screaming out at me, except my leg. All right, let's talk about another kind of exponential function where your base is not e. We don't have a ton of these examples, but you will see 1 or 2 of them in this section. Theorem. The derivative of y equals a to the x, where a is greater than 0 and not equal to 1. So this is just your general exponential function of base a, is y prime. The derivative with respect to x of a to the x equals a to the x times ln a. Now, this is assuming that you just have a to the x, because we haven't really talked a whole lot about this, but let's expand that to be the case where you have a to the u of x. Now, remember, it could be 3 to the x, 2 to the x, 1/2 to the x. It's just some exponential function. Okay, if I told you that I was in the middle of recording a video lecture for you on a broken foot, and then at 1 in the morning, my electricity went out, would you believe me? All right, I'm just going to finish this because I don't know what else to do. Luckily, I'm using my husband's Wi-Fi hotspot, and I have a cell phone light on my thing, and my laptop is charged. We're going to make it, you guys. Okay. I had been discussing the derivative of y equals a to the x. We talked about the special case where you just have a to the x. Let's then also discuss the case that will use the chain rule. If u of x is a differentiable function. Oh, well, that's not going to work here. I have a cell phone flashlight sitting on top of a wet ones wipes container. Let's just see here. You guys, e-learning is just like, it's hit a whole new low point here for everyone. Okay. Maybe. Okay. If u of x is a differentiable function, then the derivative with respect to x of a to the u of x is equal to a to the u of x ln a. Now remember, a is the base here, And then we're going to multiply that by the derivative of the function u with respect to x. So we have the special case where we just have the derivative of a to the x, and then we have another case where we don't just have a to the x, we have a to some function u of x. And then we'll look at one example of this because, like I said, you're not going to see a whole ton of this sort of thing here. See if I can maneuver this over a little bit. Example, I think we're on example 4, but I'm not even going to go back and look. Differentiate, oh, let's see. Find the derivative of y equals 5 to the tangent of x. So this is an exponential function. The base is not e, the base is a. It's a real number that's not equal to 1, and it's positive. All right, so we're following this rule. First, we're going to take a to the u, which in our case is a is 5. Maybe, I know we're not used to seeing these. So a is 5, and then tangent of x will be our function u of x. So our derivative then, y prime, is a to the u of x, so 5 to the tangent of x, times the natural log of 5, and then times du dx. So the derivative of u with respect to x is the secant squared of x because u is tangent. So we'll write secant squared x. And this is another one where there really isn't some lovely, wonderful way of writing it to make it look great. I'll just leave it like this. This is the way it is, and it is just fine. There's your derivative. Okay. The last thing I wanted to do here was just use the chain rule to find equations for tangent and normal lines for a trig function. I mean, you can do this for a whole bunch of different functions, but we'll just do it for a trig function. Because why not? I always think we need a little more practice working with our trig function values. It's never a bad idea. Example. Find equations for the tangent and normal lines of f of x equals sine squared x plus the cosine cubed of x at pi over 2, 1. Oh, sorry. There we go. Sine squared of x plus cosine cubed of x at pi over 2, 1. All right, so here's our function. Let's find its derivative. You know what? Before we find the derivative, let's rewrite the function because we have powers of sine and cosine. And to use the chain rule, it's going to be much easier to see these functions very clearly as inside and outside functions. Like that. So if I were you, I'd start out just by rewriting your function f. Once you have that, now we can take the derivative, and we're going to use the chain rule. So for our first term, we're going to take the derivative of sine squared x. We're going to bring the 2 out front, leave the inside function, decrease the power by 1. So technically it's sine x to the first. Whether you write that or not is totally up to you. And then chain on the derivative of the inside function. The derivative of sine x is cosine x. I've chained that here on the bottom. And then we'll take the derivative of cosine cubed x. We'll bring this power out front, rewrite the inside function, decrease the power by 1. Let's see if I can fix this over here. And then chain on the derivative of the inside function. The derivative of cosine x is negative sine x. Now, you don't have to do a whole ton to this. You are going to have to take f prime of pi over 2. But for now, maybe just simplify it a little bit. Not a whole lot you can do, but I would at least say this is minus 3 cosine x squared times sine x, something like that. Okay, so to find the equations for the tangent and normal lines at pi over 2, 1, we need to find the slope at pi over 2. So let's go ahead and take the derivative and evaluate it at pi over 2. Now, this one is not going to be too bad because even though sine of pi over 2 is 1, the cosine of pi over 2 is 0. Multiply 1 and 2 by 0 and you're going to get 0. Same thing here. Cosine pi over 2 is 0, square it, and you're still going to get 0. So you've got 0 minus 0, which is 0. That's your slope at pi over 2. Sorry. Slope at pi over 2 is 0. Once you have your slope, you can go ahead and use your equation y minus y sub 1 equals m times x minus x sub 1 to get the equation for the tangent line. And remember that the original point you were given gives you those coordinates for x sub 1, y sub 1. And you've done this a lot by now. So we'll have y minus y sub 1 equals m, which is 0, times x minus pi over 2. Now, the 0 just gives you 0 on the right-hand side. Add 1 to both sides, and you get y equals 1. Now, the equation for your normal line, well, I mean, think about what that's going to look like. This is a horizontal line. It's a horizontal tangent line. If your normal line is perpendicular, then it's going to be a vertical line, which has an undefined slope. So your tangent line has this equation, y equals 1, and your normal line is going to have the equation x equals pi over 2. The reason is, you know, you're evaluating or you're looking at what's happening at this point. At this point, y is 1 all the time, and x is going to be pi over 2. You know that the slope is undefined. An undefined slope has a vertical line. So if, you know, you got something happening here at pi over 2, 1, who knows what's happening with the graph. Here's your horizontal tangent line at y equals 1. If you've got a line that's perpendicular, your normal line is going to be perpendicular. Well, that has to occur at pi over 2. There's nowhere else for it to be. See what I'm saying? So don't even worry about putting in a whole bunch of thought about how to write an equation for that. That one, you'll know if the slope of your tangent line is 0, then your normal line must be vertical. And a vertical line just has the equation x equals, and then whatever coordinate it's going through. Okay. I'm so sorry that this was unbelievably crazy. I mean, I wish I don't know. I don't want to get into my day and that this is the end of my day. Email me if you have questions. I'm going to put up some homework. I think this will give you guys a really good start. And then, of course, you know, come to the office hour if you have questions about the chain rule. We're going to be revisiting it through every section in this chapter. but we're going to be using it also heavily on Thursday when we talk about implicit differentiation. So it is really the backbone of what we're going to be working on going forward, not only with chapter 3, but also with chapter 4. So let me know if you have questions. And that's it. Have a good day, you guys. You take care of yourselves.